You think you know how time works? A second is a second. A minute is a minute. The clock on your wall ticks the same whether you are sitting still or flying through space. That is what Isaac Newton told us. That is what every scientist believed for 200 years. And then a 26-year-old patent clerk in Switzerland, someone the physics community ignored, someone working a dead-end job examining other people's inventions, sat down and destroyed that certainty with a thought experiment he started when he was 16. What did Albert Einstein see in his mind that no one else could see? How did visualizing himself chasing a beam of light crack open the structure of reality itself? And why does your phone stop working without his answer? His professors at the Swiss Federal Polytechnic in Zurich locked him out of the library out of spite. They thought he was arrogant. They were not wrong. He graduated in 1900, spent 2 brutal years looking for any academic job, failed, and ended up at the Swiss Patent Office in Bern as a third-class technical expert. His job was to evaluate electromagnetic patents, clock synchronization devices, machines that used light-speed signals to coordinate time across distances. He sat at that desk and examined the cutting edge of time technology while his mind worked on something else entirely. This script is researched and factual, using sources from National Geographic's analysis of Einstein's thought experiments, published in May 2025, the Einstein Papers Project at Caltech, covering 1900 to 1909, John D. Norton's detailed historical reconstruction at the University of Pittsburgh, examining Einstein's pathway to relativity in the US, Naval Observatory's documentation of the Hoeffel-Keating atomic clock experiment from 1971. Now back to the information. If light is a wave, like everyone said, then you should see it frozen, a stationary electromagnetic field hanging in space, oscillating but not moving forward. Einstein knew instantly this was wrong. No one had ever seen such a thing. Maxwell's equations, the mathematical foundation of light and electromagnetism, said it was impossible. Light had to move at 186,000 miles per second. Always. No exceptions. This paradox followed him. He went to university. He fell in love with Mileva Maric. He graduated. He struggled. The whole time, the frozen light beam haunted him. If you chase light at light speed, what do you see? Newton said, motion is relative. You add velocities. If a train moves at 50 miles per hour and you run forward on that train at 10 miles per hour, you are moving 60 miles per hour relative to the ground. Simple. But Maxwell said, light speed is constant. It does not matter if you are moving toward the source or away from it. Light always moves at 186,000 miles per second. These two pillars of physics could not both be right. By 1905, Einstein was married, had a son, worked 6 days a week at the patent office, and was no closer to an answer. He was ready to give up. Newtonian mechanics versus Maxwell's equations. One had to be wrong. The conversation went nowhere. Einstein went home frustrated. You need a definition you can actually use, an operational definition. Suppose lightning strikes 2 ends of a train track at the same moment. How do you know they are simultaneous? Light from both strikes has to reach an observer at the same time, but light takes time to travel. If the observer is standing still on the embankment midway between the strikes, and the light from both reaches him together, then yes, the strikes were simultaneous. For him, light from strike B has to chase her down. She sees A happen before B. She measures a time gap. Both observers are correct. The strikes are simultaneous in one frame of reference and not simultaneous in the other. Observers fall out as algebra, not complicated calculus, not abstract mathematics. Just careful reasoning about what clocks actually measure. It contains 3 Einstein papers, all written that year. One explains the photoelectric effect using light quanta, the paper that eventually won him the Nobel Prize. Another proves the existence of atoms through Brownian motion. And the relativity paper rewrites space and time. He visualized. He saw the physical situation with crystalline clarity and then described what he saw. The paper ends with one sentence thanking Besso for his valuable suggestions. That single line guaranteed Besso a footnote in history. The object stays put. Each pulse carries energy. The object's total energy decreases. Now view the same event from a moving frame. The object is moving. The pulses fly off. Their speed is still light speed, but their energies differ. The forward pulse has higher energy. Matter and energy are the same thing. You can convert one into the other. The conversion rate is the speed of light squared. E equals mc squared. Einstein derived it in a few lines of algebra. 2 were friends. Lewis and Richard Keating, an astronomer at the United States Naval Observatory, bought plane tickets for themselves and 4 cesium atomic clocks. The clocks got their own seats, 2 tickets per clock. Mr. Clock flew first class. They circled the globe twice on commercial flights. First eastward, then westward. The eastward trip took 65.4 hours. 41.2 hours were spent in the air. The westward trip took 80.3 hours with 48.6 hours of flight time. Special relativity said they should lose time, but flying at altitude, farther from Earth's gravitational center, general relativity said they should gain time. The net prediction for eastward flight: lose 40 nanoseconds, plus or minus 23 nanoseconds. For westward flight, moving against Earth's rotation, the clocks would be slower relative to Earth's center, but still at altitude. Net prediction: gain 275 nanoseconds, plus or minus 21 nanoseconds, billionths of a second. But it changed. The experiment cost $8,000. $7,600 went to plane tickets. It was one of the cheapest tests of general relativity ever conducted, and one of the most direct. They measured 39 nanoseconds plus or minus 2 nanoseconds gained. Prediction: 39.8 nanoseconds. 2010, they flew around the globe, London to Los Angeles to Auckland to Hong Kong to London. Predicted gain: 246 nanoseconds plus or minus 3 nanoseconds. Measured gain: 230 nanoseconds plus or minus 20 nanoseconds. Every test works. If this is true, if time actually bends with motion and gravity, then it should affect everything that relies on precise timing. It does. The global positioning system would not function without correcting for relativity. GPS uses a constellation of 31 satellites orbiting 12,550 miles above Earth. Each satellite carries atomic clocks accurate to 1 nanosecond, 1 billionth of a second. Each satellite circles Earth twice per day, moving at roughly 8,700 miles per hour. To locate your position on the ground, your GPS receiver measures the time it takes for signals from at least 4 satellites to reach you. Those signals travel at the speed of light. If you know exactly when each signal was sent and exactly when it arrived, you can calculate your distance from each satellite. 4 distances, 4 spheres, 1 intersection point, your location. The satellites are moving at 3,889 meters per second relative to Earth's center. At that speed, time dilation makes their clocks run slow. How slow? 7 microseconds per day. 7 millionths of a second per day. That sounds tiny. It is not. Clocks tick faster in weaker gravity. How much faster? 45 microseconds per day. Subtract the 7 microseconds lost to motion. Net gain, 38 microseconds per day. That is 38,000 nanoseconds. Without correction, GPS would accumulate position errors of roughly 11.4 kilometers per day. After 2 minutes, the system would be useless. The atomic clocks aboard GPS satellites are programmed to tick at 10.2, 299.99995, 43 megahertz. On the ground, that frequency appears as exactly 10.23 megahertz. The correction is baked in. Every GPS satellite launched carries Einstein's equations in its circuitry. Your phone's blue dot exists because a 26-year-old patent clerk visualized chasing light. The mental process Einstein used matters as much as the result. He did not start with mathematics. He started with a picture, a paradox, a situation that felt wrong. He held that paradox in his mind for 10 years. He tried emission theories. He tried modifying Maxwell's equations. He tried everything conventional. Nothing worked. Only when he was desperate enough to question time itself did the answer come. And it came suddenly. One conversation. One night of thinking. One realization. Simultaneity is not absolute. His genius was in his willingness to visualize impossible scenarios and take them seriously. What if I could ride a light beam? What would I see? That stubbornness, that visual thinking, that refusal to accept contradictions, those were the tools that rebuilt physics. Massive objects pull on each other instantly across empty space. Einstein did not like that. It felt wrong. But it is not felt. Why? This equivalence principle opened the door to general relativity. If gravity and acceleration are the same, and if motion affects time, then gravity must affect time too. The stronger the gravitational field, the slower time passes. Clocks tick slower at Earth's surface than they do in orbit. Clocks tick slower near a black hole than they do far away. Gravity warps space-time itself. General relativity was published November 1915. It predicted that massive objects like the sun bend space-time. Light passing near the sun should curve. In May 1919, British astronomer Arthur Eddington observed a solar eclipse. He photographed stars near the sun's edge. Their positions shifted. The light had bent exactly as Einstein predicted. Overnight, Einstein became world famous. The eccentric genius who rewrote reality. Scott Kelly spent 340 days aboard the International Space Station starting in March 2015. His twin brother Mark stayed on Earth. The station orbits at 7,700 meters per second, fast enough to cause measurable time dilation. When Scott returned, he had aged 5 milliseconds less than Mark, 5,000ths of a second. Nothing noticeable, but real. The math works. The predictions match. Time itself is not a universal river flowing at a constant rate. Time is local, personal. It depends on where you are and how fast you're moving. Two people can experience different amounts of time and both be correct. This is not philosophy. It is not metaphor. It is how the universe works. Every atomic clock confirms it. Every GPS satellite relies on it. Every particle accelerator measures it. The proton beams in the Large Hadron Collider move at 99.999991% of light speed. At that velocity, time dilation is extreme. Particles that normally decay in microseconds last far longer because their internal clocks run slow. We see this. We measure it. Cosmic rays hitting Earth's upper atmosphere create muons. Muons are unstable. They decay in 2.2 microseconds on average. At the speed they travel, even moving at close to light speed, they should decay long before reaching the ground. They should not make it, but they do. Thousands hit detectors every minute. Why? Because from the muon's perspective, time is dilated. Their 2.2 microseconds stretch into longer durations in our frame. Relativity saves them. He saw that time itself bends. He saw it by asking a simple question and refusing to accept any answer that did not make sense. What would frozen light look like? It would not exist. So light can never be frozen? So light speed must be absolute. So time must give way. The logic is clean once you see it. But seeing it took 10 years of obsessive thought. Hendrik Lorentz and Henri Poincaré had worked out much of the mathematics. Lorentz transformations existed, but they still believed in absolute time and a stationary ether. Einstein threw out the ether entirely. Light does not need a medium. Time is whatever clocks measure. If different clocks disagree, both are right. Mach argued concepts must be tied to observations. Einstein took that seriously. He built a theory on what you can actually observe. Clock readings, light signals, measurements. Transformed time is real. All reference frames are equally valid. That was the leap. But simultaneity, the idea that this moment exists everywhere at once, is gone. We correct for them in satellites. They are real. Watch it from two different frames, compare the energies. The math forces you to conclude that mass and energy are equivalent. The object's mass decreases when it loses energy. Not by much. The speed of light squared is a huge number. You need enormous energy to change mass noticeably. But it happens. Nuclear reactions prove it. The sun proves it. Every second, the sun converts roughly 4 million tons of mass into energy. That energy is sunlight. Without E equals mc squared, we would not understand stars. We would not understand nuclear power or nuclear weapons. We would not understand the universe. Atomic clocks, particle colliders, gravitational wave detectors. They all depend on relativity. LIGO, the Laser Interferometer, Gravitational Wave Observatory, detected ripples in space-time itself in 2015. Black holes colliding a billion light years away sent waves through the fabric of the universe. We measured them. Einstein predicted gravitational waves in 1916. He thought they would be too weak to ever detect. He was wrong about that, but he was right that they exist. Einstein's genius was not magical. It was disciplined imagination, relentless curiosity, the courage to be wrong 100 times on the path to being right once. The May 1905 breakthrough happened after he told Bessot he was ready to give up. That is when insight comes, when you have exhausted every conventional path and finally consider the unconventional. That relationship mattered. Genius does not happen in a vacuum. It happens in conversation, in argument, in the friction of ideas tested against skeptical minds. Bessot gave Einstein that friction, and when the breakthrough came, Einstein thanked him in print. One sentence, enough to immortalize a friend. Electromagnetic coordination across distances. He evaluated devices that used light-speed signals to align time. This was not abstract theory. It was practical engineering. How do you synchronize clocks in different cities? You send a signal. The signal travels at light speed, account for the delay, set the clocks. But what if the clocks are moving? What if one clock is on a train? Suddenly, the practical problem becomes the theoretical paradox. Einstein lived at the intersection of technology and theory. That intersection made him see what pure theorists missed. That isolation may have helped. He was not embedded in the physics community's assumptions. He could question everything without peer pressure. He could take wild ideas seriously because no one was watching. All before he turned 27, all while working full-time at a job that had nothing to do with research. How is that possible? Part of it is raw intellectual horsepower, but part of it is focus. Einstein had been thinking about these problems for years. The ideas had been cooking. 1905 was the year they crystallized. The pressure built until the breakthroughs came rapid fire. His papers sat in Annalen Physik. Almost no one cited them. Almost no one understood them. Einstein kept working at the patent office. He applied for academic jobs. he was rejected. It took until 1909 for him to get a professorship at the University of Zurich. By then, he was 30. He had rewritten physics, and almost no one noticed. Revolutionary ideas take time to penetrate. They challenge too much. They require rethinking foundations. Most people, even smart people, even trained physicists, resist that. They have invested years in the old framework. They built careers on it. Throwing it out feels like losing everything, so they ignore the new idea as long as possible. Only when the evidence becomes overwhelming, when the new theory predicts things the old one cannot, when younger physicists adopt it, only then does the paradigm shift. Some physicists never accepted relativity. They died still believing in absolute time. Science advances one funeral at a time, as the saying goes. Old ideas die with their defenders. New ideas wait for new generations. He spent the last 30 years of his life searching for a unified field theory, trying to merge gravity and electromagnetism into one framework. He failed. That unification remains unsolved. But his earlier successes, the twin pillars of relativity, stand unshaken. We have tested them to extraordinary precision. They work. A height difference of 1 meter, 33 inches. They used optical atomic clocks, the most precise timekeepers ever built. The clock 1 meter higher ticked faster by a measurable amount, 90 billionths of a second per day faster. Einstein's equations predicted the exact number. The measurement matched. Over 1 meter. Gravity's effect on time is so precise that we can measure it across the height of a table. In 2024, geophysicist Jun Ye and colleagues measured gravitational effects at the submillimeter scale, less than the thickness of a human hair. The precision is staggering. Every test confirms the theory. Einstein saw this with his mind in 1907. He visualized a person in an elevator. He reasoned through the equivalence of gravity and acceleration. He concluded gravity must warp time. And we measure it over a millimeter. That is the lesson. The map is not the territory, but a good map predicts the territory with shocking accuracy. Einstein's map predicts time dilation to billionths of a second over a millimeter. It predicts the orbit of Mercury. It predicts gravitational lensing. It predicts black holes. It predicts the expansion of the universe. General relativity has passed every test we have thrown at it. It breaks down at the quantum scale. It cannot describe what happens inside a black hole singularity, but in the regime where we can test it, from tabletop experiments to galaxy clusters, it works perfectly. From asking the question no one else asks, from taking it seriously when everyone else says it is foolish, from sitting with the paradox until it resolves. He thought about trains and lightning and clocks, real things. Then he extracted the principles. Light from the front strike reaches her first because she moves toward it. She says the front strike happened first. Both are correct. Simultaneity depends on motion. The final piece of the mental journey is this. In 2022, researchers published results verifying time dilation effects using commercial aircraft at unprecedented precision. In 2025, new gravitational wave detections confirmed general relativity's predictions about black hole mergers billions of light years away. The tests keep coming, the precision keeps increasing, the theory holds. Quantum mechanics, dark energy, the accelerating expansion of the universe, these were discovered after his death. They complicate the picture, but they do not overturn relativity. They exist alongside it. Relativity governs the large scale. Quantum mechanics governs the small scale. Reconciling them remains unsolved. That is the next frontier. But for the scales, we can test directly, from millimeters to galaxies. Einstein's framework stands. That framework emerged from a thought experiment, a boy chasing light, a young man talking to his friend, a realization that time is not absolute. The pathway was human: struggle, confusion, persistence, willingness to question foundations, courage to be wrong, discipline to work through consequences, and finally insight that changes how we see reality. Every piece of modern technology that depends on precise timing builds Einstein's equations into its chips. Time is not what you think it is. A second here is not a second there. And once you understand why, once you follow Einstein's mental journey from paradox to clarity, you cannot unsee it. The universe is stranger and more beautiful than common sense allows. Einstein showed us how to see it. First, the Ives Stilwell experiment in 1938. They measured time dilation in fast-moving hydrogen atoms. The effect was tiny, but measurable. Then the Rossi-Hall experiment in 1940. They tracked cosmic ray muons, particles created high in the atmosphere that should decay before reaching the ground. But they make it. Time dilation keeps them alive long enough. The measurement matched the prediction. The NTS-2 satellite launched June 23, 1977. It carried the first cesium atomic clock placed in orbit. They operated it for 20 days without correction. They measured its rate. It ticked 442.5 parts in 10 to the 12th, faster than ground clocks. General relativity predicted 446.5 parts in 10 to the 12th. The difference was within error. 1% verification. The orbit was at 4.2 Earth radii. Time ran faster up there, measurably, exactly as predicted. Without relativity corrections, the errors compound. After 1 hour, positions would be off by hundreds of meters. After 1 day, 11.4 kilometers. The entire infrastructure of modern navigation depends on Einstein being right about time, and he is. That frequency is chosen so that when observed from the ground, accounting for all relativistic effects, it appears as exactly 10.23 megahertz. The offset is 4.47, 2 times 10 to the negative 10th. Tiny, critical. Without it, the system fails within minutes. The global economy has GPS timing woven through its infrastructure, and GPS has relativity woven through its design. You cannot separate them. Take out the relativity corrections and GPS stops working. The blue dot disappears. The maps fail. Everything breaks. The pathway is clear. Visualize chasing light. Realize time must be relative. Derive the mathematics. Predict the effects. Build devices that account for them. Launch satellites that prove the predictions. 120 years from thought experiment to ubiquitous infrastructure. They age about 28 microseconds per day faster than ground-based humans because gravitational time dilation dominates over velocity time dilation at that altitude. After a year aboard, an astronaut has aged roughly 10 milliseconds more. Cosmonaut Sergei Krikalev logged 803 days across 6 missions. He aged roughly 20 milliseconds more than he would have on the ground. Not less, more. Because gravity's effect outweighs velocity's effect at ISS altitude. 2024 brought new confirmations. Jonyez's team at JILA measured gravitational time dilation at sub-millimeter scales. Optical lattice clocks compared across height differences smaller than the width of a human hair. The effect was measurable. 2025 brought more. Gravitational wave detectors found black hole mergers across cosmic distances. The waves arrived exactly when general relativity predicted. Binary black holes spiraling together, neutron stars colliding, spacetime itself rippling, all following Einstein's equations, written in November 1915. Every precision measurement, they all stand on the foundation Einstein built by chasing light in his imagination. 10 years from paradox to breakthrough. 10 years of carrying a question that no one else considered worth asking. And the answer changed everything. The blue dot on your screen exists because time is not absolute. Because Einstein saw that truth by imagining something impossible. It required trusting mathematics and logic over intuition. Light speed, every prediction came true. Stating what should be observed if the theory is correct, then waiting for technology to catch up and check. That is what makes the mental journey matter beyond the physics. It shows what human minds can do, without billion-dollar equipment, without supercomputers, with just paper and thought and discipline. Einstein had a desk in Bern. He had a friend to talk to. He had books from the library. That was enough, because the tool that matters is between your ears, the ability to visualize, to reason, to question, to persist. He was not born understanding relativity. He was born curious. He stayed curious. He asked questions. He visualized answers. He tested them against logic. When they failed, he tried again. When they worked, he pushed further. The process was human. Messy. Not a straight line from question to answer. A wandering path through failed ideas and false starts, but always moving forward. Always returning to the core question. What would frozen light look like? Built from a 16-year-old's question about chasing light